Hello and welcome to another Practicalli Clojure study group. This is number 11 and we're going to look at some 4Clojure exercises today. So we're going to start with number 26, which is the Fibonacci sequence. So what is the Fibonacci sequence? Well, it's an interesting sequence of numbers used for drawing things like spirals. And let's go and have a look at the Wikipedia definition. Yeah, and then we can do search Wikipedia Fibonacci sequence. So it's essentially just this sequence of numbers. What's interesting about it is so you can draw things like the Fibonacci spiral, and you can also lay out your if you're laying out your Emacs, you can also use the Fibonacci sequence to do that as well. This idea of this golden ratio, and essentially, if you look at the numbers, you can see that each number is after the first couple, it's basically the addition of the previous two numbers. So 1 and 1. If you add 1 to itself, you get 1. If you add 1 and 1 together, you get 2. If you had 1 and 2 together, you get 3, 3 and 5 together, you get 8, and so on and so on and so on and so on. And so it's kind of like an infinite sequence. I don't believe there's an ending to it, so you can generate a whole bunch of stuff there. So we're going to work out how to actually generate that, which is going to be interesting because it's not a sequential sequence. It's not as if we can just do 1, 2, 3, 4, 5, 6, and then take out the values that we don't want, because it's a little bit more tricky than that, because it's changing each time. There's no consistent way of just removing the values except by adding like the previous two together. And this is from hello Connie. This is from this 4Clojure problem number 26. So it's asking us to write a function which returns the first X number of Fibonacci sequences. And so we've got, so we want 3, 6, and 8. So there's not a massive amount of, oops, I'm showing you the answer there. Not a massive amount of length to our sequences to pass our test. So we could actually just go in and be a bit cheeky, and if we copied the first 8 of these numbers, and then we could actually just write a simple function that would just return up to the first 8. Which is not really the goal of that, or it's of limited use, because obviously when we want more than 8, then we're a bit stuck then. Let's go and open up my editor. Let's go to GG. So I'm using Spacemacs, Emacs with the Spacemacs configuration, and I've copied the text of number 26 into my editor. What's up, kitty? The kitty outside. Kitties are talking to each other, having a discussion. And so one of these things I did think about for using Fibonacci sequences is the idea of drawing spirals in SVG, in scalable vector graphics, as one of the Clojure Bridge exercises. But hopefully we can see if we can put that in for the next event that we have. So we could just generate a range, but then it actually gets a bit tricky to actually figure out how to pull out the values. So it's not as just simple as generating a range and pulling out just the ones you want. If we took the sequence here, this is our Fibonacci sequence, and we could just be a bit naughty and write a simple little function, that takes a number in. So it's like a series. So that's how many numbers we want to see in our Fibonacci sequence. And then we just do take a series from a vector that contains all the numbers. And if we then put this into, so this is defining the function. If we then want to put that into a function call, that function definition into the first part of in the first element of a list, and then the second element just needs to be the value of the length of numbers. So if we do that, then obviously we get something that's going to work. So this would actually work for our test. If we go back to our, where's it go? Yeah, if we go back to our Fibonacci sequence, and we actually put in here, instead of that answer, we could just put in our new very simplified, let's get rid of that old example, very simplified way of doing this, and I think this should work. I haven't tested this, but let's see. Oh yes, oh look, it all passes. We actually get quite a low golf score, which shows you how pointless the golf score is. I don't want that food, no. Oh yes, so that's actually my best. Oh, there we go, cool. Let's go back to the code. So that's a very hard code way of solving the problem. I mean, it gets it done. But again, if we wanted to do anything more than 8, we would be in trouble because that would no longer work. Well, or it would not produce the right amount of values. Actually, I wonder what would happen if we do 9. Yeah, so if we do 9, it still returns the sequence of 8 numbers, which is not entirely wrong, but not entirely correct either. But it does help us solve the problem and go and look at the people's solutions if we want to. However, it's better to kind of, it's an opportunity to think about what else we can do to generate these numbers. So one of the things we can look at, if we look at the, go back and look at the Fibonacci sequence itself, if we can see it in the tests, it's always starting with 1, 1. So that's a pattern we can detect. So we can actually just set up our tests just to start with 1, 1. So whatever number of sequence we're going to generate, we can always have 1, 1 as the start. So if we were going to go and just do the simplest way of not cheating, I mean, is to have this Fibonacci function. It's going to take the lengths of series in there. And we can see that here we're just returning 1, 1 regardless of whatever it is. So that will always kind of return. So if we wanted a Fibonacci sequence of 2, then this would always give us the right answer. And for anything else, that wouldn't be very useful, but we can expand on this as well. So let's see. So this is how we would call it. So we call it with 2. And then we got the right answer. The problem is if we call it with 3 or anything else, then we're not going to get the right answer. 1, 1. So we need to be able to return the sequence based on the size that we're actually going to acquire. So let me just a bit inconsistent in my aiming here. So here we've got our starting Fibonacci sequence of 1, 1. and if the count of this series is less than the length of the series, then we need to iterate. Otherwise, we can just return the fib. So we're assuming here that we can return, we're going to return at least a Fibonacci sequence of 2 or greater. So now we need to figure out how we're actually going to iterate around this and to actually generate the right number. So how do we do this? We could just do a loop or a recur. I think I did a recur here. Let's see. So yeah, we're going to. So if we, if the Fibonacci sequence is less than the actual size, the length of series, then we're actually going to call this recur. So it's going to call itself. So it's going to call this loop again, and it's going to pass in the fib, and it's going to also reduce over adding the fib together. So the fib in here is going to be 1 and 1. So we can add 1 and 1 together to return 2. And so this would actually give us like the first 3 values for definite, because it's going to go in, return this, and it'll return the value of those 2 things added together. So we've defined this function and we're calling it now, and we call it with an argument 3. And so let's actually debug this and walk through this so we can see exactly what's actually going on. So I'm going to do a comma db to set up a kind of breakpoint, which will allow me to step through the Fibonacci sequence. So you can see where things are highlighted. So here we've got the local name fib highlighted, and this is showing you what its current value is. So we've got this loop where our fib value is just 1 and 1, and then that's of size 2, which is actually less than size 3, which is the size that we've passed in from down here to the argument of this function. And then that's so it is true that the fib size is smaller than size. So then we're going to recur to get another value. So this is taking the fib value, and it's going to add the fib value together. So it's going to add 1, 1 together to get 2. And then it's going to conjoin that value into the original fib value and pass that back to the loop. So we're going to get 1, 1, 2 back there. Then the fib size is that. The size is 3. So that's going to be false because the fib size is no longer smaller than the size. So therefore, I'm just going to do the false path, which is the next line down, which is just returning the current value of fib, which is 1, 1, 2. And so that test would then pass. So this function would then pass for the first test. So our first test was for 3. So this would actually just return the right result for that first test. Just double check that. So if I so this should pass the first test, but fail the second and third, I think. Yeah, so it passes the first and then fails the second and third because we're only doing, we're not really adding up. We're not doing anything intelligent except just adding the first 2 values up, essentially. And so we need to add a little bit extra logic into there to make this work. So let's see how we did that. So yeah, you see if we do generate with a 6, then we get this value of 1, 2, 4, 8, 16. So it's kind of getting there, but it's not quite right because we're not really adding the right numbers together the right way. So it's something that is a sequence of numbers, but not the Fibonacci sequence. So we need to change the way that we actually do this recur and make it a little bit cleverer. So rather than just taking the all of the values, so here when we do a recur in this function above, we're adding 1, 1, 2, and then we get 4, rather than adding 1 and 2 together. So we're actually taking all the numbers when we only want to take some of the numbers. Actually, the last two values of the Fibonacci sequence we want to take, and then that generates the next one, and then we would take those two to generate the next one, and so on and so on. So we need to just, rather than add specific numbers up inside when we're doing our recur. So we're still going to start off with our basic Fibonacci sequence. We're still going to check the size, but this time we're going to, when we're generating the next number, we're going to add together the last value in the Fibonacci sequence. So from this, and we also want to have the second to last, but there's no second to last function, so we have to basically create our own second to last function here. So if we reverse the Fibonacci, then the last becomes the first, and the second to last becomes the second. So we can use the second function to be able to get that value from the Fibonacci sequence, and then we can just add them up. So now when we're going to recur, instead of adding all the numbers up, we can just add the last two numbers up, and that will give us the right sequence value each time. So if we add here, we've got our, so we're adding those together. We've put this into a function. Let's call it, let's just double check that that is true. Oops. Oops, oh yes, sorry. I deleted that by mistake. There we go. So we're generating numbers. So we're adding 1, 1 together, and we get 2, 1 and 2 together, get 3, 3 and 5, and so on and so on and so on. So that is our Fibonacci sequence. If we go and put this back into 4Clojure, and we should be able to now pass all of these tests. Let's see. Yes, they're all green. Excellent. Happy days. So it is quite a low-level abstraction. We are using a loop recur. It's fairly efficient because we're using recur, so we're not going to, we could run this and generate quite a large sequence without worrying about blowing up the memory in our computer, because recur is generating, is overwriting the calculation each time, or the memory that we use to generate the calculation each time. So we're not growing the memory space inside our computer to be able to generate a really long list. So we have like, we wanted like 100,000 or like a million, or several million kind of long sequence, then we could actually generate that without it blowing up our memory in our computer. So it's a very simple approach. It's I think it's very clear, but there are possibly other ways we can do this using some of the other functions in Clojure. And once we've solved it, we can also go and look at some of the solutions in there as well. But we'll come back to that in a moment. Is there any questions so far? Oh, Kant's got a question. Have you got a question? Maybe. How would you want to solve this? You know, solve it with reduce. Do you want to try some reducing? Oh yes. Okay. Let's do some reducing in there. Let's go back to our editor. Yeah, so we've been using loop recur, kind of classic, simplest way to kind of do stuff. Gives us a lot of power. But there's also functions called reduce. So reduce is one way to generate a sequence of values from things, or actually a particular value from a sequence, should I say. So if we evaluate these, so reduce will basically take this function and use it to basically work on each element of these this vector and produce a result based on applying the function. So here we're actually going to add, essentially adding up each of the values together, and we get 4. One way to actually see what it's doing step by step is to use something called reductions, which is going to show you, in simple terms, it'll actually show you the working out of reduce, how it's got to where it's got to. So again, a very simple example, reductions. So it's the same thing as reduce, but we're just using reductions with the same arguments. And we can see now that it's actually showing us our working out. So the first value that reduce would create would be 1, and then it would add 1 to it to get 2, and then it would add 1 to 2 to get 3, and then it would add 1 to 3 to get 4. So reductions is actually showing us all the values that reduce is going through, but reduce will only show you the result, whereas reductions shows you all the values, basically showing you how it got to the result. If we do that in a bigger example, and okay, that's a big number. Are we sure that that's the right number? Did we get it? One way to look at this is if we see if we can actually see all the steps it went through to get there. And so, yeah, when we're multiplying 1, we get 1, multiplying 2 with 1, we get 2, multiplying 3 with 2, we get 6, and so on and so on and so on and so on. So we can see all the calculations step by step on how we actually got to those values. Reduce and reductions are quite useful for us to learn, and it's quite useful to see if you're not sure what's going on in reductions can actually help elaborate that all those actions as well. So reduce might be reproducing different results than you expected. So you can also look at reductions to kind of see what's actually going on inside. And both of these functions actually can take a starting value, which is handy for our Fibonacci series because we have a starting value of 1, 1. So here we've got reduce. It's going to start with the empty vector, and it's going to conj everything into the empty vector. And if we show this in reductions, we can see how it's built up that final result there as well. So let's have a look at applying this to our Fibonacci sequence. And so we've done this, it's kind of the same thing. If we actually look at this, where we're basically taking 2 values and we're going to make another value by adding the first and second value up, essentially. So here we're adding the first value and the second value together, so that would give us 2. And so the first time round in this loop, it would give us a 2 value, which we're going to add. And we're going to dismiss, this underscore just means to ignore the other values. So we're only going to take the first and second value in this, but we're going to put this within inside of reductions, which means we're going to generate everything, all the results. And we're actually going to be using those results, all those different combinations we're going to generate to be able to pick out actually the right values, because it generates a lot more values than we actually want in the series. Actually, it turns out that the results of these things, if we take the first of every kind of pair of results that we generate from this primary and secondary, the primary value is actually the sequence of Fibonacci that we actually want. So we can just map this first function to just grab the first value from the result of reductions, and then we can be our Fibonacci sequence. So if we actually look at the reductions in a little bit more detail before we go into this, see if I can make this work. So size of series, if we do that to 8, for example, 9, because range is exclusive, so 1 to 8 will generate the numbers 1 to 7. Range 1 to 9 will generate range 1 to 8. Oh, I don't want to do that. There we go. There we go. This will generate the range 1 to 8, like that. So that's just the range expression. It just generates 1, 2, 3, 4, 5, 6, 7, 8. We've got our function. We've got our seed value for our Fibonacci function, and this is just doing what they call. I've gone blank on the name now. What do they call this? But basically pattern matching on the arguments for the arguments. So we're just going to take the first and second value and add them all up. And then if we give this, if we put this into yes, there we go. So here we're generating a range of values by adding the primary and secondary up. So you can see that the values in here. So we got 1, 1, we got 1, 2, 2, 3, 3, 5. So we're adding the numbers together. 3 and 5 gives 8. 5 and 8 gives 13. 13 and 21 gives 21, 34, and so on and so on. Oops, sorry. There we go. And actually, if we look at this, so if we take 1, 1, 2, 3, 5, 8, 13, 21, and 34, you can see if we take the first value of each of these vectors, we actually get the Fibonacci sequence. So that's what we're doing with this map first. We're just actually going to map first over this sequence of values. So if we actually take that and we do that, rather than talk about it, let's just actually do it. So map first over, oops, go on. So that's not going to work because we need to quote it. There we go. And if we evaluate this, hopefully we should get the Fibonacci sequence. There we go. So this is how this is working. So we're generating a whole bunch of combinations, and then we realize that those combinations, the first value of each of those is actually the Fibonacci sequence that we want. So we just extract that from those values, and we return the result. And let's see. We put all that together and we test it with 8. A Fibonacci sequence. But let's actually just kind of walk through that a little bit as well with the debugger. So db, just instrumenting this function. So size of series is going to be 8. And so it's going to generate the numbers 1 to 7. And then we're basically taking the secondary, which is 1, ready, and we're going to add those two together, numbers together, we get 2. We're basically going through here to add all the numbers up that we're going to put into our reductions. The reductions takes all those values and basically adds them together. So it's returning those as these two value vectors each time, and then we can then refine that down to the actual Fibonacci sequence. And there we go. And then we just return it. There we go. There's the answer. So I quite like this approach because it's quite a common way to kind of generate the data set that you want that simplifies the simplifies the function that we're actually trying to get. So here we're just getting the first value of each of from each of these vectors inside our collection, which is a very simple thing to do in Clojure. And so we actually generated this data set that we want, that we know we can apply a simple function on to get the right results. And I think so I quite like that. It's a very data-centric approach. Whereas when we take the loop recur thing, we're actually being a bit more explicit in how it's all working. So we're like stepping through. So it's a little bit more iterative, and it's less, I guess, less declarative in the approach. Whereas reductions was just saying, generate this value, and then from these generate this sequence, and then from this sequence just extract the values that we actually want. So it's less prescriptive and a bit more functional in that way. Is there any questions? No questions so far. Excellent. So lip recur is the one thing I used, and then let's see. So we're reductions. So this is the function we've used here. I'm just going to tidy this up so I can onto GitHub. There we go. So let's do the. Oops. So this is our reduce approach. And we've got our hard-coded answer as well. And I have actually seen a CoreLogic one, but I think that deserves a broadcast in itself, because CoreLogic is really powerful, but it does take a little bit to get your head around and how it all actually works. So I'm going to skip that one for now. And there is a whole bunch of other approaches to do this. That's just a sorted set. Is there anything interesting I came up with doing this? No. I don't think there's a whole bunch of other things out there on the internet about different ways to solve it as well. So feel free to go and explore different ways. But yeah, essentially a lot of these are very similar. So this is just a function calling itself, which is just one step above, really, like a loop recur. In fact, you could just put recur in there and it'd actually still work and actually be memory efficient as well. And then if we go and have a look at the 4Clojure, now we've solved it, we can go and look at the solutions. So if you don't have this solutions thing, it's probably because you're not following anybody. So if you go into top users, then oops, that's taking a while to load. There we go. And you can just go and follow people, and the people you follow, you will see their solutions that they've come up with. And again, some of them are interesting, some of them are the same as what you've got, and some of them are very, very different and not always kind of better or worse than yours. So again, have a look at them as a way to learn rather than to identify the perfect solution, because everything has context anyway. So Jetrel is a good one to follow. I think it's Mike Fikes is in there somewhere as well. But yeah, I'm just following just random people from those who have solved pretty much all the problems, really. But there are some weird and wonderful. Oops. There are some weird and wonderful answers. So take the answers with a pinch of salt. So let's go and look at the solutions that people have come up with. So this is my solution, or a solution, the last solution I pasted in. And yeah, somebody else is using reductions here. Somebody's using a lazy sequence there as well, and concatenating things together. But generally, the general form is pretty much the same. Again, that's the business logic of Fibonacci. You're adding the last two values together and generating either generating specific the specific result, or you're generating all the possible results and then narrowing it down to just the results you actually want. That's just the same loop recur. So I don't think there's anything else that's different here. Just slightly different takes on exactly the same functions as well. There's somebody just kind of using the bare minimum. Which, yeah, if you're in a startup and you kind of know for a little while that that's the only thing that people want to use, then that's fine. It can save you time, but obviously you need to, yeah, be well aware of the limitations of this kind of approach. And this is a bit better. This is taking, so this is actually still generating, it's iterating over, creating all the iterations of these combinations and mapping the first. So this is, yeah, a slightly different way of writing the writing the reductions approach that I did. So that's quite interesting, actually. Yes. Well, there we go. Okay, and oh yes, so that's yeah, it's kind of the same as using a cond to set up the first few values. So if you wanted a Fibonacci sequence of 0, of 1, that's assuming you're starting this Fibonacci sequence at 0. And if the length of the sequence you want is less than 3, then you'll just return 1s as well. Yeah, okay. So there's a bit of interpretation about what is actually where it starts, but as a test show, they all start with 1 1 in this case to make the test work. There's a bit of a threading macro approach there, which is quite interesting. But essentially, they're all the same. I don't think there's too many unique ways. The most different way of doing it would be to do something like core logic as well. Okay, let's see if there's any questions. There's no questions there. Is there any questions? It's very quiet on the Hangout, so obviously Manny's busy today, so there's nobody else in the Hangout. No, nope. Okay, so we've still got a bit of time, so let's go and look at the next problem. I think the next problem is fairly straightforward once you've kind of had a little bit of a think about it. So, oops, let's hide the answer. There we go. Hope you didn't see that too quickly. Let's make this page a little bit bigger. So this is palindrome detector. So a palindrome is basically something that's the same forwards is backwards. So 1, 2, 3, 4, 5 is not the same, but if you had 1, 2, 3, 4, 5, 4, 3, 2, 1, then that would be true. But this is just 1, 2, 3, 4, 5. So if we reverse this, then it would be it would be 5, 4, 3, 2, 1, which is not the same. Racecar is a palindrome because it's if you reversed all the characters in there, then it would be true. And if we reverse foo bar and foo, that would be the same. That would still be foo bar foo. So the numbers, and then ABC obviously is different as well. So it does. This is an easy one, not that elementary one, but it's a fairly easy one. But it does give us this nice hint, and this comes down to how Clojure by default treats a string. So it's giving us a hint about this particular thing. So if we just used reverse, so let's hide that. Let's come back to that for a second. Just use reverse in there, so we reverse the function there. That might just pass the first one, but then we'll see what actually happens with the second one as well, because that would be quite nice if it was just reverse. That would make it nice and easy. Oh, that's failed all the tests. Okay, interesting. Let's have a look. 27.027. Palindrome And and the nice thing about Emacs is if we create a namespace with a dash in it, it'll change the name of the file name for us. So this is just palindrome underscore detector. So if we just reverse a list of 1, 2, 3, 4, 5. Is that failing then? Interesting. Oh yes, because we need to generate false, don't we? Yes, so we can't just use reverse. Well, it does reverse the number. It's not comparing the two. So we need a function that would take in the number, and then we compare the number. Oops. There we go. Compare the number. With the reverse of the number. This one, there we go. So if we give that an argument, a function call that function, we can call it with this value here. And let's see what we get. We get false. So if we, rather than just using reverse, we're doing the comparison. So we need to do with the comparison ourselves. We take this number, boom, 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 and let's put this into our, where was it? Oh, there it is. Here we go. We put this into 4Clojure. It's a big function, not too worried about a goal score or anything like that just yet. So we've got our number. We're going to take the number, which is the argument. So this will be 1, 2, 3, 4, 5, and Racecar and Fibonacci and so on. And then is that number equal to the reverse number? And it'll give us this equal sign will give us a true or a false. There's a little bit like writing a little unit test essentially. So the first one passes, but the second one fails. Oh, and maybe it's something to do with this Racecar and the way Clojure treats a string. But we got the first one passed, so that's a step in the right direction. So let's go and look at see what happens when we use Racecar as an argument. Oops. So if we take this and we, instead of this value, we use a string called Racecar. And then let's see what actually we get. So, boom, boom, boom. So we're still getting false, but we're supposed to get true. This is supposed to be the same. And so when we do something with Racecar, it's not quite working. So let's have a look specifically what we're doing there. Hello, kitty. What's happening? Oops, sorry, let's reverse. We want to reverse Racecar. Oh, the cat's sticking my foot now. Racecar. So there we go. So this is what's actually occurring. So a string is actually treated like a collection in Clojure. And so it's actually treating it as a collection of characters. So the /R and the /A and the /C, they're all characters, and they're no longer a collection of values, they're individual character values. So we can't just use reverse because the Clojure reverse in Clojure.core is just going to treat them like characters, and we can't compare a string with characters by themselves. So we could either break down the Racecar string into a sequence and reverse it, or we can recombine Racecar into back into a string. Let's see, did I still have that? So this is I think this is the answer I came up with, and this is quite a low golf score kind of approach, but let's break it up into something a little bit more readable. Let's see. So we've got a function number. My cat wants to type on the keyboard now. You're slobbing all over my hand. Thank you very much, kitty. So there we go. Cat-driven programming isn't always the most efficient. There we go. Sorry. There we go. Now we're lying all over me. There we go. Thank you. Thank you, kitty. Hello. So where was I? So I'm taking a sequence of the number, which will, like actually specifically turn something into a sequence. So, so here, it returns a sequence of a collection. So we take number. So let's just go and have a look at what sequence does. So sequence is kind of a way of thinking about collections in a more abstract way, just as a sequence of values. So if I do seek, go on, off you go. Go on. Cat stopping me typing. Sorry, there we go. Seek of string Racecar. Oh, there we go. So it's actually producing the actual sequence. So this is kind of what's happening underneath when we do reverse. It's actually it's dealing with the sequence of Racecar rather than the string of Racecar. So we can do both, so then if we can then compare the result of sequence and reverse because they've generated the same kind of information, the same structure of information, in that they've then compare the characters that are in the list, this collection, rather than comparing a string with characters. So our sequence number, is that equal to the reverse of the number? So that's, oops. So that should work. And we're using number here, but that's like just I guess that's the value rather than number. I should have really put in there. So let's go see if this works in 4Clojure, which it should do, I think. So it's going to treat everything like a sequence. That way we should be okay. Should deal with the string case specifically. Let's see. So it's passing. Yay! Cool. So that works, and that gives us a nice short form. And this is just a short form if you were if you're at all worried about your golf score, which you really shouldn't be, then that's just a shorter way to do that. If you're going to map a function once over a collection inside another function, then this can make it a little bit simpler to read the function that's included in the map. But yeah, if you want to be very clear, then using the full normal form of a function is a little bit more clearer sometimes. Oh, there we go. Yeah, so there's a question, what does it mean when you use hash and plus insert? Let's delve into that just a little bit more detail as well. So I can write a function. In fact, I've written a function here, and it's taking an argument. So a function, I can also give it a name. I can also give this function a name called John, or what is it doing? Compare. Or actually, no, it's palindrome really. Palindrome. So if I was going to do that, and I could also, if I wanted to share this function between all the other functions in this namespace, if I wanted to use it more widely, then I'd make this a defin rather than a function. If I use a function, then I have to call it inline. So if I actually want to call this definition, I have to then put this into a bracket and give it some numbers. So I'd have to do 3, 2, 1, and then I could call that. Oops. And I could also boom. So I'm kind of going up the level of abstraction. So if I called this, if I did defin palindrome, then I can then call it as a separate function from anywhere inside my code. I can palindrome. Oh, I haven't evaluated that. Let's see. Yes, let's just evaluate that. There we go. So I can evaluate that, and it creates that name of the function inside the namespace. Oops. Now I can call that from anywhere. Type. There we go. And give it the same. Then we can just give it an argument. Actually, no, there we go. 2, 3, 1, and then call that true. Or I can go the other way, and so write a function. So if we call this function inline, we don't actually have to give it a name. But I can't actually, if I evaluate this, it's just going to give me the definition, but I can't call it. That's why you need to put this into a list. But if you use this function, then you can just use it inline. And this is just a shortcut way of doing function. And rather than having an argument here, we're just assuming there's going to be an argument that it's going to pass in or not as the case. And we're going to represent the first argument, which you could do this as well. So this is showing we're going to take the first argument, which is number in this case. So we'll still need to wrap this inside a call. And if we slurp that in there, and then we still need a value to pass into that as well. Put our 1, 2, 3, 2, 1. We're going to call this inline function, and it's going to take the first argument, which is just the whole vector, and the second argument it's going to take the first argument again here as well. So this is what the percent means. It's a placeholder for where the argument goes, and the percent is just a shortcut for doing the first one. So if you just see percent, it's just going to get you the first argument. If we had multiple arguments here, let's do what makes sense. Oh, it's just 1, 2, 3, 2, 1. We could then have argument 1 and argument 2. Yeah. So this is argument 2 and this is argument 1. We're passing into this function call, just like if we had in here, if we had number 1 and number 2, oops, then we'd have to have, oh, actually, let's do that. In this one here, so number 1, number 2, and then if we had this again, there we go. So this function is going to, we call this function, it's got number 1, number 2, and then we'd have to specify obviously number 1 and number 2. There we go. So this function now is the same as this function here. This is just a shortcut way of doing things. So this is basically saying this is a function call, and I'm going to drop its entire kind of structure. So I'm not kind of calling it. Let's see, let's delete that word. But I'm not going to define it's a function. The fact that I'm putting this hash around in front of the list means that I'm defining a function call, so that it's going to expand into this function with arguments, and we're actually just putting in the body of the logic here into it. So this is essentially the same as this sequence here. So it does the identical kind of thing. So it allows us basically just to write the kind of business logic without writing the actual function definition specifically around it. Again, it's when you're using inline functions, it can make something a little bit easier to read, but sometimes it can make it more confusing as well until you get used to it. I hope that answered your question, Connie. Let's see. So this is often referred to as like syntactic. Oh, sugar. Oh, sugar now. These are both, yeah, so these are both function definitions. So they both need to be called in there. So they meant to be used inline inside another function, really. And you can also return a function as well as a result. But yes, it's usually when you're doing things like mapping and filtering, you might take this form just to basically focus on the fact that this is the business logic that you're actually applying to a collection. And once people are used to this hash notation, then yeah, they just realize that this is a function that we're applying to it, and you save a few characters. But there we go. Okay. I wonder if there's any other interesting ways to solve this. Let's go and have a quick look at 4Clojure, and so we've got a working solution. Again, we could put in the short form to reduce our golf score if you were concerned about that. But again, it's not that important. Somebody's put in a bit more defensive programming here. They're putting a cons statement in there. So just checking if it's a string, then we are going to apply that. This might be useful if there's like a performance overhead or a significantly notable overhead of like having to apply string. Well, in this case, this wouldn't work with the other solutions, but because if you apply string to the other ones, you're going to turn them all into a string, and they're not going to equal. So this is basically saying if it's a string, then when you reverse the string, apply this str function on that, and this will turn the result of reverse string back into a string. So you'll be able to then compare the original string with the newly reversed string, and the newly reversed string is a string instead of a sequence of collections. And if it's not a string that you've passed in as an argument, then you can just reverse it. So if there's a specific case, a specific type of data or form of data you need to work in, then this cond is helping take care of that unusual case. Or it might even be that one case is quite unperformance. You want everything to work by default in this approach because it's really fast, and then you occasionally get one condition where it's slow, and you have to kind of do this other approach as well. This is the short form of solution. Vec in this case is kind of doing the same thing, I guess, as seek, in that fact that it's turning the string into a vector of characters. So it's essentially doing the same thing. It's a more specific version of seek in this case. Seek will just turn it into a sequence, which will actually be as a list. Vec is turning it specifically into a vector. So if you needed to have your data in a certain form, then that might be something you need to do. But seek is probably like the more general approach you would use. And these are just, this is just the long form of writing in a function, and so on and so on and so on. And I guess applying list is the same thing as doing seek and vector. Well, it's a longer way of writing this. So it's basically applying list to the string, turning it into a list of characters. I think that's it. I don't think there's anything particularly else you can do. This is interesting. This is quite a imperative way of doing things because you're basically just specifying exactly what's going on. So you're just going to go in and compare the first element of the last element, and so on and so on and so on, and keep on recurring around. And if you put a break in this, then it could be, you could add some optimization so that you don't end up comparing the whole value to see if it's a palindrome, because if the first and last characters are not the same, then you definitely know it's not a palindrome, so you could actually stop there. So if you were going to deal with very, very large palindromes, so in when you're dealing with words, then there's going to be a finite list of what a palindrome is. I mean, unless you're counting, you could actually have like a sentence that is a palindrome as well. Or I think it would be a bit challenging to write a really, really long piece of text that is still a palindrome. But that could be another way to, you could write a program to do that, I guess. So there's kind of I think there's, for most palindromes, when you think about words, then yes, I think it's probably, you don't really need to worry about like breaking out of the comparison, unless you want to write the world's fastest palindrome checker. You probably don't need to worry about that. Okay, I think that's all there is to be said about that one too. There is some quite involved approaches. So there we go. Oh, we're splitting here as well. One thing I wanted to check just quickly before we leave this one. I think there's so when you're dealing with strings, there's usually there's this Clojure.string library, and is that got to reverse? And that's got to reverse. So if I reverse Racecar here and actually evaluate this, then it's actually returning the value Racecar. So this is another way to actually deal with strings. So if we have, so if we have a function that takes in the value, and so we can then do the check to see if it's a string. Oops, if let's see if it's equal as a string. So is the value of value a string? Is the type of value a string? And then if it is, then we can do equals value, and closure string slash reverse, and then reverse the value. So that should work. That should give us a working comparison. And then let's put that in the right place. There we go. And then otherwise we just do value versus value. So for everything else, we can just use the reverse and compare them that way. So that'll be another way to do it. Again, I think that's quite nice and explicit. You can see that we're reversing a string. We're not having to worry about the fact that we need to break it down into a list of characters. So I think that's why I quite like the Clojure.string library, because it's a nice abstraction when you want to deal specifically with string values. There's some nice specific functions that will deal with strings and keep them as strings, so you don't have to worry about breaking them down into a sequence of characters. Okay, well, that's the hour. That's what I've been trying to kind of keep these broadcasts to, so I may stop there unless there are any further questions. I'm just going to have a quick look to see the next exercise is in 4Clojure. So let's have a quick look at number 28 and see. This is something, if we don't cover it, we can do for homework as well. Yes, let's do this one for homework. So if you want to have a go at doing this, so you want to write a function which flattens these sequences. So if we take this here and should put this at the end of here. Boom. Let's put it in. So is that? Have I missed the thing? Put that into a. So what function can we write that makes, oh, that doesn't seem to be, oh, okay, I haven't stubbed it in enough, have I? What function can we write to make this a flat structure? Oh. So it's saying we can't use flatten, which usually means that that's an answer that will work. So if we use flatten, and then we get a result from there. Oops, did I? Oh, wrong arguments. Let me kill that. I think I copied. This is a danger in copying and pasting things wrong. Get the wrong values. Okay, right. Yes, I copied too much in there. There we go. So that's, oh yes, so it wants to be, did that? Oh yes, flatten. Yeah, there we go. Copy. Too many. Oh, that's not good. Get there eventually. Yeah, copy and pasting is can be tricky with structured editing. There we go. So we've got a collection of like a list, and then a single value, and then a vector, but it's got another vector nested within it, and we just want to produce a single collection with just all the numbers without any kind of nested values. And so flatten should give us the right answer. There we go. So there we go. But the problem is this exercise doesn't allow us to use flatten. So we have to kind of come up with a function that will do that. So I'm going to go through that in another broadcast, but feel free to have a go at that in your own time for a homework as well. Ooh. What? Let's look. We've got some questions on the chat. Let's see, doing a function but didn't work. Let's have a look. Let me just go and see if I can find the chat and copy in the is that the chat? No, that's the wrong chat. There's the chat. Oop. Me, let's see me. There's my chat. Let's see. Let's kind of take these. Copy. Let's see if we can have a look, see what's going on. As in. Okay, that's before I forget, I'll put that back on. So this example, wrong number of arguments passed. Oh, yes, we don't have an argument. So if we put in a return there, so this is our function, and we're calling it with inside a list. Oh, where's that function? Oh, okay. It's a function. That's the close function. Okay, so we need to. Oh, we're using both forms. Okay, so you don't use both forms together. So if you would take, so let's take, let's take this. So to fix this one, we would pick that over there and put that in there. So that should work, and then we need to give it some arguments. So we need 1, 2, 3, I think. I got that wrong as well. What did I do? Oh, yes. Okay, so that would be A, B, and C. And that would work, but that's going to print that on the onto the REPL. So that's doing 1, 2, 3 down there. If you go back here, space window, maximize. So rather than print line, let's change that to string, which is very similar, but it'll actually show us the results in line 3. So yes, I can appreciate you put a function inside. Oh, actually, I wonder if that would work. I've never actually tried to use a function with inside a function. You still need to put an argument there of 1, 2, and 3. Might work, although it's complaining about something. Oh, no, that's not quite. You don't need to do that. So you would need to. Oh yeah, you don't need that. The other way of writing it would be that. Oops. And then there. What? I've got that. I've got too many arguments. There we go. Space. And There we go. That'll be the other way. So these are two ways of doing it. There we go. Boom. Yeah, so if I change that to string, it's the same result, but it'll print it in line as well. 23. Those are two different ways of doing that. And is this the same? More or less the same. What's this complaining about? Oh, the functions. Is this just one, two, oops. Is that right? Is that all I need to do? Oh. Okay. Oh, that's interesting. Just a point of note. This is starting to use the nicer kind of spec notation for error messaging. So it's starting to give you a bit more interesting values, interesting information when you've got errors. And so this is quite nice. Insider. So what do we get? If we take a function, and then we're going, because we're calling a function. Oh, okay, right. Yeah, so we've got a function that's calling a function that we've written. Okay, 1, 2, 3. That's not right, is it? Yeah. So these are two ways I'd write those. So you can either use string or print line. String will return the result. Print line will put that onto the command line. Sorry, yeah, either on the command line or the onto the REPL. But yeah, because I don't usually have the REPL on there, then yeah, that looks right. Yeah, yeah, because you're taking those functions in on string. Did that work? Ooh. Yeah, you don't need the anonymous function. There's no kind of real value in using the anonymous function in there. Let me just. So I would either use one or the other, not one inside the other. Just go and pick the nose. Where is it? Boom, boom, boom. Oops, why can't we do? There you go. Could be that. Yes, I suppose if you just unwrapped this, just remove the outer. Oops! Oh, did the wrong one. To remove the outer the brackets, then that would evaluate. I believe. Let's see. It's not going to evaluate because that's. Yeah, because we're using one or the other. Yeah, so you can. I've got yeah, they just need to be inside there. Yeah, so that's so you don't need both forms in there. So you can either use this function, or you would use this. A, B, and C. And then, so that's the function definition, and then to call that, you would do, oops, into brackets, and then you would do 1, 2, and 3. So these two are equivalent there. Back, I think. There we go. Cool. Yeah, so it's I would kind of stick with just using functions, or if they're going to be in line. If you're doing that inside another application, if you want to actually define a function, because these are this bit is exactly. Let's see if we, let's see. Make this nice and clear in my own mind. So if we get rid of that, and okay. So this is defining function, and then this is calling. And that's the same for that. And this is different. So this is the normal form of defining function, and then we just put that in brackets to call the function, and then give it any particular arguments we've got. And this is defining function, and this is how we call that function with arguments as the short form, as the is actually called a reader macro. So this will actually expand when this closure is read. It actually just expands it to this syntax, this code. So it's just a shorthand way of writing it, but in the end, this function definition, this function call, so this definition would be straight away converted into this code when Clojure reads it, and this function call here would be converted into this function into this code as soon as Clojure reads it as well. So this is mainly for the developer to write a terse, a smaller bit of code should they actually need to, and should it actually make the code easier to read. Alrighty. If there aren't any more questions, then I'm going to leave it there. Thank you very much for listening. And if you have any suggestions about what we want to see next week, then please get in touch either on the Slack channel or as comments on the meetup or comments on the broadcast. Thank you very much and see you next week. Bye-bye. Whee!